Hello students, welcome to Lecture 7, Isotopes and Atomic Mass. Let's first discuss isotopes. Isotopes are atoms of the same element with the same number of protons and the same atomic number, but a different number of neutrons and a different mass number. So let's see two examples of two isotopes of nitrogen down here, N14 and N15. But before we do that, let's remember that in notations like these, remember that the top left number always gives you the mass number, the bottom left number always gives you the atomic number, that the number of protons always equals the atomic number, and that the number of neutrons equals the mass number minus the atomic number. All right, so let's analyze each of these isotopes of nitrogen. So for N14, this bottom left number tells us that the atomic number of nitrogen 14 is 7. And this top left number tells us that the mass number of nitrogen 14 is 14. We also know that this atomic number of 7 tells us the number of protons in N14. Since the atomic number 7, that also tells us that in N14 there are 7 protons. To find the number of neutrons in N14, we just do the mass number 14 minus the atomic number of 7, giving us 7 neutrons in N14. Now for N15, this top left number tells us that the mass number of N15 is obviously 15. This bottom left number tells us that the atomic number of N15 is obviously 7. And this bottom left number of 7, which is the atomic number, also tells us the number of protons. Since the atomic number is 7, that tells us also that in N15 there are also 7 protons. And finally, to get the number of neutrons, you just do the mass number 15 minus the atomic number of 7, giving you 8 neutrons in N15. So as you can see here, based on what I just analyzed, the mass number and the number of neutrons are different for these two isotopes of nitrogen, while the atomic number and the number of protons are the same for these two isotopes of nitrogen. All right, so that's an example of two isotopes, N14 and N15. Now let's discuss isotopic notation, or 4 ways in which isotopes can be written or represented in chemistry. Let's use the example of the isotope carbon-14. So the first way to represent an isotope is to write a superscript as the mass number, and then follow that up by the element symbol. So for carbon-14, write the superscript 14 first to represent the mass number 14 for carbon-14, and follow that up with the symbol C to represent the element carbon. The second way to represent an isotope is to write a superscript as the mass number of the isotope, a subscript beneath the superscript as the atomic number of the isotope, and then follow that up with an element symbol in the middle. So for carbon-14, write the superscript 14 to represent the mass number of carbon-14, which is 14. Write the subscript of 6 directly beneath it to represent the atomic number of 6 for the isotope carbon-14, and follow it up with the symbol C in the middle to represent the element carbon. The third way to represent an isotope is to write the chemical element's full name, usually from table S, followed by a dash, followed by a mass number. Okay, so for carbon-14, write carbon as the element's full name, write a dash, and then finally write the mass number 14 after the dash to represent the mass number of the isotope carbon-14. The fourth and final way to represent an isotope is to write the chemical element symbol from either the periodic table or table S, followed by a dash, followed by the mass number. So for carbon-14, write C as the element symbol to represent the element carbon, a dash, and write the mass number 14 after the dash to represent the mass number of the isotope carbon-14. All right, so these are the 4 ways to represent isotopes using isotopic notation. Now let's practice with isotopes. In the first question, we have 2 pairs of isotopes, here and here. A lot of this is review, so I'm going to go through this really quickly. Okay, email me if you have any questions. So the first pair is uranium-235 and uranium-238. I want to know right now, for your convenience, that uranium symbol is U. So there you go. So make sure you use that information. Now, to find atomic number, look at the bottom left bold number in the element box in the periodic table. The atomic number of uranium, or U, is 92. And since you have 2 isotopes of the same element, uranium, you know that you have the same atomic number. You also know that since we can assume this is a neutral atom, since I said nothing about an ion, you can assume it's a neutral atom. Since it's a neutral atom, we know that atomic number equals the number of protons, and also in an atom only, the atomic number also will equal the number of electrons. Using this, since we know that the atomic number is 92 for both uranium isotopes, we also know that there are 92 protons and 92 electrons for both isotopes as well. All right? Now for nuclear charge, you have to take the number of protons for each of these isotopes and add a plus sign at the end. Since both isotopes have 92 protons, adding a plus sign, we see that both uranium isotopes also both have the same nuclear charge. Both of them have nuclear charge specifically of 92 plus. Okay? Now the difference between these 2 isotopes is in the number of neutrons as well as in their mass numbers. So note the type of isotopic notation here for both uranium isotopes, where in each case, the element name is followed by the mass number after a dash. Using this, we see that the number after the dash for this first isotope tells us the mass number for uranium-235 is 235. And the number after the dash for the second isotope tells us that the mass number for uranium-238 is 238. So there we go, there are mass numbers. Now finally, to find the number of neutrons for each isotope, just subtract the mass number minus the atomic number. So for uranium-235, we have the mass number 235 minus the atomic number 92, or 143 neutrons, sorry. And then for uranium-238, we have 238 as the mass number minus 92 as the atomic number, leaving us with 146 neutrons. So there you go, there are a number of neutrons. All right. Now finally, for the last column, you have to write the isotopic notation using mass number in the top left, atomic number in the bottom left, and an element symbol in the middle. So writing in this notation for uranium-235 and uranium-238, we get the following. Uranium-235 has 235 as the top left mass number, 92 as the bottom left atomic number, and the symbol U for uranium. And then for uranium-238, we have 238 as the top left mass number, 92 as the bottom left atomic number, and the symbol U for uranium. Okay. For these next two isotopes, 2010Ne and 1810Ne, notice that these isotopic notations give the mass number in the top left number, the atomic number in the bottom left number, and the element symbol in the middle. So based on this, we know that the atomic number based on the bottom left number in both cases would be 10, right? Next, we know that for neutrons that the atomic number equals not only the number of protons, but also the number of electrons for neutral atoms only. So since the atomic number is 10 for both neon isotopes, we also know that we have 10 protons as well as 10 electrons for both isotopes of neon. All right. For the nuclear charge, just take the number of protons and add a plus sign. Seeing that we have 10 protons in both cases of both isotopes, adding a plus sign, we see that we have a nuclear charge of 10 plus for both isotopes of neon. Now, we know that the isotopes differ in their mass number and their number of neutrons. So to find the number of neutrons, just take the mass number minus the atomic number. For the first isotope, we have the mass number of 20 minus an atomic number of 10, giving us 10 neutrons. For the second isotope, we have a mass number of 18 minus the atomic number of 10, giving us 8 neutrons. So there we go. All right, now we have to explain why each pair represents different isotopes of the same element. Each pair represents isotopes of the same element because they have the same number of protons and the same atomic number, but they differ in their number of neutrons and their mass number. So the next question says, explain in terms of subatomic particles why uranium-235 and uranium-238 represent different isotopes of uranium, right? So notice here that it's in terms of subatomic particles, so we have to discuss protons, electrons, and or neutrons in our answer. Obviously, we know isotopes have the same number of the subatomic particle proton, but they differ in the number of the subatomic particle known as neutrons. So our answer here is they are isotopes of the same element uranium because they have the same number of protons, but they differ in their number of neutrons. That's how we define isotopes using subatomic particles. Specifically, if you look up here as a point of reference, you'll notice that uranium-238 has 3 more neutrons than uranium-235 does if you look in this column right here. All right, the last question asks us to find which notations represent different isotopes of the same element. Note that each notation shows the element symbol in the middle like this, the mass number is the top left number, and the atomic number is the bottom left number. And we know isotopes must have the same atomic number, but different mass numbers. So if you work off that criteria, only the first 2 options fit, because in both cases, these are the only cases in which each isotope has the same atomic number or same bottom left number, but a different mass number or different top left number. All right, the third option is wrong because both forms of Al have the same atomic and the same mass number, so that doesn't fit. And the last answer is wrong because the atomic numbers are different. And this kind of question will pop up on your homework, and it'll also ask you to explain why. Just use this as your explanation, okay? Next, let's discuss atomic mass. Atomic mass is the weighted average mass of all naturally occurring isotopes of an element, and it's measured in units of AM, U, or U, as you should add to your homework. An atomic mass of an element is always written in decimal form rather than a whole number. As you can see, the atomic mass in decimal form is listed on the periodic table for each element in the top left corner of each element box. One important distinction I want you to know about atomic mass versus mass number is atomic mass is based on the weighted average mass of all naturally occurring isotopes. On the other hand, mass number is only based on the number of protons and neutrons in one specific isotope. So this has to do with all naturally occurring isotopes and a weighted average mass, while mass number only focuses on the number of protons plus the number of neutrons in a specific isotope. All right. Next, note that the atomic mass unit, AMU, is a unit defined as 1/12 the mass of a single atom of carbon-12. Okay? Finally, I want you to note a relation between moles and atomic mass. Specifically, when you're given the atomic mass in grams, what you should know is that atomic mass in grams of the element represents the mass of 1 mole of atoms of that element, which we'll see in a minute. All right, so for example, the atomic mass in grams of carbon, which is listed on the periodic table as 12.011 grams, would be the mass of 1 mole of atoms of carbon. All right, so let's try 3 examples now really quickly. The first example says define average atomic mass. Obviously, as we see up here, the average atomic mass, or the atomic mass, is the weighted average mass of all naturally occurring isotopes of an element. Number 2 says which quantity equals 1 mole of Ag, atomic mass in grams, atomic number in grams, mass of neutrons in grams, or mass number of neutrons in grams, sorry. Here we see that the answer is atomic mass in grams because we know that the atomic mass in grams of silver, which is listed on the periodic table as 107.868 in the unit grams, represents the mass of 1 mole of Ag atoms. All right. Finally, this third example says find the number of neutrons in the nucleus of an element with an atomic mass of 190. For a problem like this where you have the atomic mass and you have to find the number of neutrons, but you don't know the identity of the element, all you have to do is find the element with the atomic mass given using the atomic masses on the periodic table. Once you identify that element, then you have to use the atomic mass as a mass number and subtract from it the atomic number of the element you found from it to find the number of neutrons. All right, so in this example, we know that the element with the atomic mass of 190 is OS because OS's atomic mass listed on the periodic table is approximately equal to 190. So then what we have to do is we have to take 190 as the mass number and subtract from it the atomic number of the element we found, which is OS. OS's atomic number is 76. So if we plug it in here, we get the number of neutrons. Here is 190 for the mass number minus 76 for the atomic number of OS, gives us 114 neutrons in this problem, okay? So there's your answer there. So make sure that you use this hint for similar types of problems. Next, let's talk about how to approximate average atomic mass. First off, atomic mass is closest to the atomic mass of the isotope with the greatest percent natural abundance. For example, if 90% of the isotopes of an element have an atomic mass of 100, while only 10% of the isotopes of that element have an atomic mass of 98, which one do you think it's going to be closer to? Obviously, the average atomic mass would be closer to the atomic mass of 100, since most of the isotopes have an atomic mass of 100 anyway. Also here, when you're approximating average atomic mass, use the periodic table to find the average atomic mass and then compare it to the atomic mass of different isotopes to see which one is most abundant. Whichever whole number it's closest to tells you which isotope is most abundant. All right, for example, let's try an example here. Let's say we have 2 naturally occurring isotopes of vanadium, vanadium 50 and vanadium 51. The atomic mass of vanadium listed in the periodic table is 50.9415, right? Which is closer to, as we can see if we round it, closer to 51 than 50. So that tells you that vanadium 51 has a higher percent natural abundance than vanadium 50 does. Because obviously this atomic mass is closer to the atomic mass of vanadium 51. So that implies that vanadium 51 would be more abundant since this is closer to it anyway. Okay, now let's discuss calculating average atomic mass. To calculate average atomic mass, just use the weighted average of all isotope masses multiplied by their natural abundances. All right, so yeah, the formula is for this that I want you to use all the time when calculating average atomic mass is average atomic mass is equal to the percent of isotope 1 times the mass of isotope 1 plus the percent of isotope 2 times the mass of isotope 2 plus product so on for specific isotopes until you get to plus percent of isotope n times the mass of isotope n. And the sum of all these products is divided by 100. All right, so let's try an example here. Here we have chlorine's 2 isotopes, chlorine 35 and chlorine 37. Chlorine 35's atomic mass is 34.969 U and percent abundance is 75.77. Chlorine 37's atomic mass is 36.966 U and percent abundance is 24.23. The most common isotope of chlorine using percent abundance is chlorine 35 since it has the highest percent abundance. Think of percent abundance as a measure of how common the isotope is in a selection of many naturally occurring isotopes. Now the atomic mass based on the percent natural abundance will be closest to 35 U since the percent natural abundance of chlorine 35 is higher than chlorine 37's. Remember, average atomic mass is always closest to the atomic mass of the isotope with the greatest percent natural abundance. Last, to calculate chlorine's average atomic mass, we write average atomic mass of chlorine is equal to percent of the first isotope, chlorine 35, which we see is 75.77%, times the mass of chlorine 35, which is 34.969 U, plus the percent of the second isotope, chlorine 37, which is 24.23%, times the mass of chlorine 37, which we see in the chart is 36.966 U. Then we divide the sum of these two products by 100, getting us the average atomic mass of chlorine, 35.453 U, which we see listed on the periodic table as the atomic mass of chlorine. Last, let's calculate natural abundances of isotopes. If you're given atomic masses of isotopes and the average atomic mass, how do you find percent natural abundances of each isotope? Well, for most problems, you'll get two isotopes, and for that, you use this very simple three-step process. Step 1, treat one isotope's natural abundance as x and the other's abundance as 1 minus x. It doesn't matter which you assign to which because you'll get the same answer no matter which you assign to which. I also wanted to note, by the way, that 1 minus x and x are used as natural abundances because their sum is 1, the whole number equivalent of 100%. All right, step 2, plug into the equation for average atomic mass, but without dividing by 100. Then solve for x and 1 minus x algebraically. By the way, here you don't divide by 100 because you treat each percent as a decimal. And this is the same as dividing whole number percents by 100% anyway. All right, what it might look like is, for example, with average atomic mass, you would get average atomic mass is equal to, let's say, 1 minus x is the abundance of isotope 1 times isotope 1's mass, plus x, which we designated the abundance of isotope 2 times isotope 2's mass. And adding the sum of those two together, of those two products together, you get the average atomic mass. All right. Step 3, finally, once you find the answer, convert the decimal to a percent by either multiplying by 100 or moving the decimal place 2 spaces to the right as you learned in algebra. Let's now try an example. Here we have boron's atomic mass of 10.81 AMU from the periodic table and two isotopes. Boron 11 with atomic mass 10.013 AMU and boron 11 with atomic mass 11.009 AMU. And we have to find the percent natural abundances of each of these isotopes. So step 1, I let boron 10's natural abundance equal x, and boron 11's natural abundance equal 1 minus x. All right, step 2, average atomic mass of 10.81 U for boron is equal to B10's natural abundance of x times B10's atomic mass of 10.013 U plus B11's natural abundance 1 minus x times B11's atomic mass of 11.009 U. If we multiply x by 10.013 and 1 minus x by 11.009 using the distributive property, we get 10.81 U is equal to 10.013x plus 11.009 minus 11.009x. And if we combine like terms, we simplify this to get 10.81 U is equal to 11.009 minus 0.996x. Right, then you just solve for this algebraically by subtracting 11.009 both sides, getting you negative 0.996x is equal to negative 0.119. Then to solve for x, you just divide by negative 0.996 on both sides, getting you x for the natural abundance of boron 10 is 0.199, which as a percent is 19.9% boron 10. For boron 11, we have an abundance of 1 minus x, or 1 minus 0.199, which equals 0.801 as boron 11's natural abundance. As a percent, boron 11's natural abundance is 80.1% boron 11. So our answer is boron 11's natural abundance is 80.1%, and boron 10's natural abundance is 19.9%. Okay? So finally, please complete these homework questions, or these practice questions on your own in addition to the notes you just took. Thanks. See you tomorrow.